In this video, we will finish up our discussion of dimensional analysis and start talking about how we can use prefixes. To finish up dimensional analysis, we talked about in the last video that you cannot have units in the arguments of any cosine, sine, any of the trig functions, or of exponential functions. So I'm going to show you how we can use that to learn something. In this thing, we have a set of radioactive nuclei that happens to follow this formula. N equal N naught times e to the minus time divided by this tau, which is some sort of constant. And the question would be, is like how to interpret that tau. I.e., what is the units of that tau? What is that constant telling us? Well, the units here, for instance, if we're talking about nuclei that decay, the units of this are nuclei. And the units of this are nuclei. The units of the argument of this exponential must be unitless, and the exponential itself must come back unitless. So what this is telling me is that the units of t divided by the units of tau, which is seconds, divided by the unit of tau, assuming that I choose to measure t in seconds. Sometimes I'll measure it in days, years, or whatever. Must be unitless. Well, that means that the units of tau is seconds. So tau has the units of seconds. It's a constant. Well, if it's a constant who has the units of seconds, which are times, it makes sense that we call tau the time constant for this decay. And in fact, it's related to something called the half-life. So by observing and looking at equations, not only can we check our work, but when we're looking at experimental work where we don't know the equations, it actually gives us a guide on how to find the laws of physics. So whether it's an engineer trying to do a new design or whether it's a physicist trying to develop an entire new field of engineering, we get a lot of information out of units. So you need to become an expert with working with them. Now, we work with very widely different sizes of quantities. In fact, for instance, the resistivity in the semiconductors and modern electronics can vary by 40 orders of magnitude. That's 1 with 40 zeros after it. All right? So we can deal with the very small, we're dealing with single atoms or even a quark, for instance, to huge when we're dealing with the universe in physics. So we need to have a way to deal with large numbers because human beings don't do well with large or small numbers in our head. And we need to be able to make quick mental calculations. So how do we do that? We deal with what are called prefixes. So to make rough calculations, to make practical and safe designs, we need to find a way to work with numbers. And what we've done is we developed a set of prefixes and a thing called engineering notation. There's also something called scientific notation, which is related, but I don't think is as powerful as the engineering notation. Well, the few times I will ever say that, actually. And most of the time, generally the scientific stuff is stronger, but not in this case. And we restrict, this enables us to restrict all the numbers that we have to multiply or work in our head between 0.1 and 999.999. In other words, basically between 1 divided by 10 and 1,000. And I can do those calculations pretty quick. 500 times 2 is 1,000. 500 times 3, that's 1,500. What I do not do good is what is 38,952 times 0.00057. Okay? We're not going to deal with that. We're going to deal with numbers like 3 times 2 and use these prefixes to enable us to work with these numbers that we can do quickly. So let me show you how we go about doing this sort of stuff, prefixes and scientific notations. So the first thing to do is go back and review scientific notation. We have something that's a very large number, 325,500 meters. And I want to do a couple of things here. Usually in chemistry they talk a lot about significant figures. What that means is that when one's measuring this, there's some uncertainty. And in looking at this, the way we go about it is that we say any number that's not a 0 is significant. So 3, 2, 5, 5, those are all significant. But these last two, they're not. And what that means is I'm saying that this number, 325,500, is uncertain to plus or minus at least half of this number, half of 100. So plus or minus 50 meters. Well, what if you'd have measured that to 1 meter? Well, how are you going to tell me that? Well, that's a problem. This is another reason that we develop what's called scientific notation. In scientific notation, any number that you write down is significant. And the way we do that is we do this. We take the dot here and we move it to the left. 1, 2, 3, 4, 5. And we write down 3.255. And you can write zeros if they're significant, meaning if this is where the uncertainty is, if you don't know this to 50, you stop. If you didn't know this, no, I measured this to 5 meters. It's only this one I didn't know. I really did measure that 0. Then you could put a 0 here and make that a significant number. If, on the other hand, you'd measured this to half a meter and this one you actually knew, then you could put another 0. Every number you write down in scientific notation is significant because we're not just using this, like right here, to tell me where the decimal place is. That's the way, by convention, we believe those zeros were put there. We believe you just put them there to tell me that that's where the decimal place went. Then we write times 10, and to get this number back where we started, I have to tell you how many places I moved the decimal to the left. 1, 2, 3, 4, 5 places. Now, while this is somewhat useful, why is it useful? Because now instead of multiplying 325,500, I can multiply 3.255. That's about 3. And I can multiply 3 times some other number like 2, and that's about 6. That's a little bigger than 6. But I still have this times 10 to fit, this 100,000 that I have to remember. And I'd like to kind of get rid of that if I could. All right, so anyway, that's scientific notation. Hopefully you've covered it previously. The idea is to be able to write one of these big numbers to both show the correct number of significant figures and also to be able to make it where this number is not so large so that the number only has 3.255. By the way, it would be okay if you wanted and sometimes to put the decimal here and make it 0.3255 10 to the 6. But most books, most people say to do scientific notation, you leave one non-zero number non-zero digit to the left of the decimal. Let's try another one. Write the following number using scientific notation and the correct number of significant digits. Now, in this case, this 0 is not significant. It's just there to tell me again where that decimal place is. But this one, I didn't need it to tell me about where the decimal place was. It must mean that you actually measured that digit on some sort of meter. So this one is saying that this number is 0.3250 meters plus or minus 0.00005 meters, half of whatever that is. That's in. So this was measured really small amount. That's not a meter. Okay, so if we went back, that'd be a centimeter there. That's a millimeter there. And that thing looks to be 50 microns, or about something on the order of the size of a human hair. So you measured something that was about a third of a meter long, a little more than a foot, and you measured it to the size of a human hair. Now, how would we write this in scientific notation? We would simply move the decimal one place, this time to the right. And to indicate it went one place, but that it went to the right, we put -1. Again, hopefully you've had this previously in other courses. All right. Again, notice that it makes it easy to multiply, 3.25. But again, I've still got to remember this 10 to the minus stuff over here and how to deal with that. What is the difference between that and what I called engineering notation? The difference in engineering notation is all exponents must be multiples of 3. So you do not have to just have one digit, non-zero digit, on the other side of the decimal. The number has to be between 0.1 and 1,000, but you can have more than one digit next to the decimal. What is different is that your exponent must be a multiple of 3. So let me show you an example here. I can only move it in groups of 3. So I can move it 3 places. 325.5 meters times 10 to the 3 meters. That would be okay. That would be one possibility. That's within 1,000. I also could move it not 3, but move it 6 places. And it could be written as 0.3255 times 10 to the 6 meters. Either would be okay. I might say that on many calculators, they have built-in capability to put it into engineering notation. Now, it doesn't look to have any advantage over scientific. The advantage has to do with this. I'm going to be able to use prefixes to eliminate these times 10 to the whatever. That's what we're going to do in the next video. We're going to use prefixes to get rid of those times 10 to the whatever and enable us to write this in a more compact form that enables us to do calculations in our head quicker. All right. Now, it's just one more example before we go to the next video, although it's not in your notes, so you would have to write this one down. How about if we had this number 0.0000057 meters? So that's the new example. Well, if I was to do that one, again, I'd move it 1, 2, 3, so I can even move it 3. But when I moved it 3, if I look at that, that's going to be 0.057. That's not acceptable because that number's not within 0.1. So I need to move it 3 more. So that's moving it 10 to the 6. So the answer should be 57, there's my period, times 10 to the minus 6 meters. This would be engineering notation. 5.7 times 10 to the minus 5 meters, that would be scientific notation. Scientific notation, you only have one non-zero digit to the left. In engineering notation, the difference is that this exponent has to be a multiple of 3. It can be either 0, 3, 6, 9, 12, 15, so forth. But it's got to be a multiple of 3. All right, we'll deal with prefixes in the next video.